Okay, let's start the next session. Next speaker is Ian Lewis. Please start. Let's start.
All right, thank you. I'm going to be talking about deep learning with Python and TensorFlow. So this is room 201, so if you're going to be tweeting and that sort of thing, then you should probably use the underscore PyConJP underscore 201 hashtag. So I'm Ian Lewis. I'm a developer advocate at Google. I have been involved with the Python community for quite a number of years. I'm one of the original 4 founders of this very conference. I haven't really done very much for it recently, but I started it with folks like Terada-san back in 2010, 2011. Today, I'm also based here in Tokyo, so if you guys are in town and want to have a drink or whatever, then just send me a message on Twitter, or if you had feedback after the talk, that sort of thing. Yeah, I'm a PyConJP person, but I also do things like Go, and recently I've been very involved in things like the Kubernetes community and Docker and containers, things related to that. But today I'm going to be talking mostly about deep learning and TensorFlow. So before I go into actually talking about TensorFlow, I want to give a little bit of a background into deep learning and what it is, and why it's important. So deep learning is a type of machine learning. So I know that many of you are probably familiar with things like machine learning, but deep learning is specifically kind of a keyword or a buzzword that many people use to talk about machine learning, but it's really specifically talking about a certain type of machine learning. And machine learning, what it's talking about is specifically neural networks, and not just neural networks, but deep neural networks. So I'll explain a little bit about what that is in a little bit, but essentially what neural networks are very good at are things like classification and regression problems. So classification is a type of thing, is a type of problem where you take some input and you put it into a number of one of the predefined buckets. So like you say you have like different buckets like A, B, C, D, and you want to classify it one way or the other. An example of this might be spam or things like that, where you mark it as spam or no spam. There's only 2 buckets. But there are other examples, such as attaching labels to things, where you have many, many more buckets. So what does that kind of look like? So if the network cooperates, we can look at a simple problem. So here's a simple classification problem. Let me zoom out here. So maybe you have something like this, where you have some data, and you want to be able to classify this. So this is actually a really easy problem, right? You have 2 sets of, or 2 different groups of data. You have, say, like some, and this x and y might be the height and the weight of a person. And so you want to graph this and then say like whether the person is an adult or a child, right? And you have some data that says that these are adults, these blue ones are adults, and these orange ones are children. And any new data that you get coming into it, you want to be able to classify them as either adults or children. And so you can do this fairly easily. All you really have to do with this particular problem is just draw a line between it, or down the middle of it, in order to classify the adults and children. So we don't even necessarily need any hidden layers there. We can just straight up draw a line between the 2. But what if we get into like more complicated problems, like say this spiral? Maybe you have some sort of data that represents something that's much more complicated. In these cases, you'll need something that's much more complicated in order to actually have it learn and figure out what the actually I need to give it a little bit more different inputs. And so you need to give it a little bit more make it a little bit more complex. You need to have a little bit more complex of an algorithm in order to be able to classify a set of data points like this. So even still, it's not really doing a great job, but it's a lot closer than it would be if I wasn't building something like this, this more complicated neural network. So this is something that's like 3 layers deep, but let's actually talk a little bit about what that means. Oops. Let me go back here. So what is a neural network? So a neural network is essentially a type of machine learning problem where you break the problem up into these kind of layers. And at each layer, you'll basically perform some sort of activation function on the input coming into that layer. So here we have just a 3-layer network, and where we have this blue layer, which is the input layer. This might be some data that you get in, like say a cat picture, and then you put that through a simple this single hidden layer, which will do some sort of activation function on the data, and then you get an output layer, which is this cat, or maybe a label or a different type or a bucket. In this case, it's a single value, so it might be just a percentage chance that this picture is a picture of a cat. So, what are these layers made up of? So, these layers are essentially, the parts of a neural network are essentially a bunch of matrix multiplications or matrix operations. So, what you have here is you have something, an input piece of data. So maybe you have a picture. You take that picture and you transform it into a data structure called a tensor. A tensor is very similar to a matrix, and I'll talk a little bit about that later. But essentially, what you do is you can take this tensor and then you can run a number of activation functions at each individual hidden layer, and then get an output in the form of a tensor as well. So like each of these is like a matrix multiplication. You get a matrix, you send a matrix in, you multiply, you get a matrix out, maybe it's some different dimensions, and then you continually do that throughout the network until you get the output, which is also a tensor. So what is a tensor? A tensor is something that people talk about a lot in these machine learning systems, but I think it's much easier to talk about something like a matrix that people are more familiar with. So you can imagine a tensor as a point or a value in a multidimensional space. So with something like a vector, maybe that's like a 2-dimensional space, right? And a matrix might be a 3-dimensional type of space where you have like some sort of point or value. Whereas a tensor is a multidimensional. It could be any dimensional. So you could say a vector is a type of tensor, or a matrix is a type of tensor. But a tensor could be any number of dimensions. It could be thousands or even millions of dimensions big. But essentially what you can do with these tensors is, as long as the tensors that you're multiplying together, the same as with matrix multiplication, as long as the dimensions match for these particular tensors that you're multiplying together, you can multiply them same exact way that you would a matrix. So to give you an idea, like we often see these kind of like little network diagrams of what a matrix or a neural network looks like. Say we have this input x value. This is a tensor, and these are the values inside of the tensor. So you have like, in this case, it looks like something like a vector, right? You have like just 3 values within the tensor. And these are x1, x2, and x3. And then we're going to multiply it by this W tensor. And this W tensor is a weight, a tensor that defines a weight for that particular layer in the network. And each of these values in this W tensor is a value, or each of these are a value inside the tensor. So what we're doing is we're taking one tensor here, this X tensor, we're multiplying it by this W tensor, and then we're going to then add it with this B tensor, which is a bias tensor. So this is a pretty typical example of what you do in a single layer of a neural network, where you take an input tensor, multiply it by a weight, and add it to a bias. And then you might do this multiple times throughout the network. And then at the end, a typical thing you would do is run a softmax. So generally what you'd get out of this is you would get a bunch of values in a tensor. And these values are basically kind of a relative value. They might be a relative value for whatever you're talking about. And that might be, say, like just some number, like 120. And then in another one might be like 20.345 or something. And these are things that are like fairly meaningless to people. But once you run it through something like a softmax, this softmax function will actually will normalize the data so that you get out a value between 1 and 0 as output. And so you can think of that as, say, we get out this output tensor, which is this y tensor. This might be, say, the percentage that the input value fit into a single bucket. So say this is like cats, dogs, and birds, right? You give it a picture, you run the activation function, and you get out a percentage that it fits into each bucket. And then you can say, okay, well, the one that it fits the most, has the highest percentage of fitting in, is the bucket that I want to put it in. That's essentially what you're doing. Okay, so that's how like neural networks work, right? Like we're giving some data in, we're trying to predict which bucket it goes in. But how do you actually train a neural network? You have to be able to train it on some sort of data to begin with, right? So this is just a diagram showing how you might train a model. So what we have here is we actually have, in this bottom half of the diagram, we have the actual, our neural network. So this is the network itself running, and we provided some input values. This is actually like a 2-layer network. And you get out some value. So this is actually the network itself. But then what we're going to do is we're going to take some training data. So this training data is essentially some input values and labels that specify that are basically the same exact format as the output that you would get out of your network. So in this case, our training data would be something like these 3 values here. And maybe you're giving it a picture. The training data is a picture of a cat. Okay, so we have a picture of a cat, and we know that that's a picture of a cat, so we're going to have a 1 in the cat column, and then a 0 in the other, because we know that it's not a dog and it's not a bird, right? So that's the training data. And then what we do is we run it against a loss function. This is called a loss function, which is basically taking the difference, or the idea is that it takes the difference between the value that you expect, which is the 1, 0, 0, the cat. It's a 100% chance that it's a cat, to the actual output that you get from your neural network. And the neural network might say 60% a cat, 30% a dog, and 80% a bird. So it got it wrong. It thinks it's a bird. But we want to get it to go closer to what we had in the labels, or at the label, which is a 1, 0, 0. That would be the ideal. So what we do is we run it against, we take the diff, which is the loss function, which gives you a value for how wrong you are, and then you run that against what's called you run that through a gradient function, which will then tell you how to change your model, or how to change the weights and the biases that you use in your network in order to make the output be closer to what you want. So this is the basic idea, is that you run it through this loss function, you take the diff, you update your weights and biases, and then you propagate that, or back-propagate that, back into your neural network. So what we're doing here is we're updating the weights and biases that we use in the network. And these values get then fed back into the weights and biases here. So these are the exact same values that we're using here, down here. So we do this over and over again. So you can imagine that we're giving it data over and over and over again to train this model. And we're continually updating the weights and biases to get it closer and closer to the value that we want. Okay. So that's a background in what deep learning and what training models and what the models actually look like. But so why are we actually even talking about this? Like, why is this a big topic recently? Like, you seem to hear like machine learning coming out, or machine learning people, showing up at conferences and giving talks and things like that. Like, why is this something that we're talking about right now. And the reason for that is that recently we've had a number of basically breakthroughs in building these models and actually doing something useful with them. So this is a model of, or this is a diagram of one of the models that we use at Google. This is the inception model, and this is used to train or label images. We have a model that will label images with many tens of thousands of labels. So you can imagine that we have a neural network that will give us, we put it in an image and we get out a tensor that's like tens of thousands of values big. And each one of those is a probability that it fits into a single bucket, right? And then we can figure out what the top 5 labels is or something like that, right? So this is what the model looks like. And you can imagine that each one of these is a layer in the network, right? And each one of these is essentially a matrix multiplication or a matrix addition or something like that. So if you can think with me, just imagine with me that we have quite a few number of these individual layers in the network, or these individual functions that we've got to run. And if we go back here, you can see that each one of the values that we put in, you can imagine each one of these being like the RGB values, or like you might have RGB, so 3 values for every single pixel that you have in an image. And maybe that image is 5 megabytes big. And then you give that, you multiply that with a matrix, however many number of times that we have this, that we have boxes in this image, right? And each one of those matrix multiplications might be a 5 megabyte image, 3 values for each pixel for each 5 megabyte image, and you multiply that times a weight and bias in another matrix that's maybe tens of thousands or maybe even millions of values big. So you can imagine how many matrix operations there would be to do just one of these boxes. And then you're going to run it through all of these boxes. And then you're going to do that 1.5 million or tens of millions of times. You can imagine how much processing power that might be. Okay, so that's a lot of processing power. Why do we have to do that? So the reason that we have to do that is because with traditional models and with small and medium neural networks, the more values that you give it, basically these models don't scale. Essentially what it is that you have a traditional learning algorithm, say, where you give it some data, and it basically peaks right about here, right? It doesn't really get very far before it's basically maxed out. The more data, if you give it more data, it's just not going to get any smarter. And some small and medium neural networks are a little bit better, but it's only when you really get to large neural networks where it starts scaling to produce values or accuracy that's somewhat meaningful, that can actually solve problems that are close to what humans can do. So we basically can't make, like, say just cut this in half and just, deal with it by doing less work, because we don't get enough accuracy. We don't get the value that we want out of it. So we have to have these large neural networks. But training them is very, very difficult. So what people do is they tend to use GPUs a lot. They use, but it still takes hours or days or even weeks to train a model, because you have lots and lots of data that you have to train with it. So people use things like supercomputers instead. So like when I go to Python conferences, I ask people how many people have access to supercomputers, how many people have access to a supercomputer. Anybody can use a supercomputer in this room. This is actually the first time that nobody's raised their hand. But usually it's like 1 or 2 people, right? And but not many people have access to these supercomputers, right? You don't really have if you want to train a large model, you need some way of doing that. And generally what we've done to solve that is to somehow distribute that training across a bunch of different machines. So that's something that we've done at Google. So we've applied these type of machine learning algorithms to a lot of different things, like picking out where in images there is some text, so that we can figure out how to change that text. Like first you identify where the text is, and then you can take that text data and change that into actual text. So that's the image data, and then actually change that into actual text, and then say like, okay, now we know where the McDonald's is for things like Street View. You can then classify things like everyday objects like bananas and oranges, things like statues, etc. So these are things that can like actually solve real-world problems. And so I mentioned that these are breakthroughs, basically, but we've only been able to really do these things fairly recently, right? This is a graph of the number of projects at Google that use machine learning. And you can see that after 2014, like before 2014 was like more or less linear growth, right? But then once you get to 2014 or the end of 2014, you have this like hockey stick of like all of these projects starting to use machine learning. And the reason for that is because we've actually been able to distribute this training and then figure out how to build models that can actually do real-world work. And part of that is actually because we've built something called TensorFlow that allows us to distribute the training and to get it to work and actually solve problems much more easily. So to actually get into the real part of my talk, so TensorFlow is an open source library that is built for machine intelligence. It's written in Python, or it has a Python. It's a Python library with a C++ core in order to basically make the calculations fast. It's like a fairly typical pattern with Python libraries, but essentially what it does is allows you to break up these different parts of the models, so like the different layers and things like that, into operations that can then be mapped to CPUs and GPUs or devices where you can actually do the calculations. So some of the core concepts are graphs and operations in tensors. A graph represents this kind of graph structure with all of the operations inside of it. Operations make up the graph, so they're basically a node in the graph. And then the tensors are basically the data structures that you are passing between the different operations in the graph. So this is where we get the idea of TensorFlow. We have a tensor that is then flowing through different operations within the graph. A couple of concepts are constants and placeholders, variables and sessions. So constants are essentially what you would imagine. They're values you can't change. Placeholders are basically inputs into your neural network. So you can imagine these values down here at the bottom, these little green values, those are placeholders. Variables are the things that vary as you train the model. So you can imagine these weights and biases, those are the variables. And then you have a session value which encapsulates a training session. So this is just a non-exhaustive list of all the operations that are built into TensorFlow, but the main ones you kind of know about are like things like multiplication, addition of the tensors, and that sort of thing. But you can do quite a lot. So let's actually show what this looks like. So I'm going to run through an example here. This is the amnesty tutorial. Let me actually blow this up a little bit if I can without making it look really awful. So what I'm going to do is restart and clear this. So this is basically MNIST is a very typical training. It's a very famous kind of training set or public data set. And what it is a bunch of handwritten images or handwritten images of numbers. And then what we're going to do is we're going to perform OCR on these numbers to figure out what number each image is or what's written in each image. So what we're going to do here is we're going to let's see, shift. No, it's control enter. Gosh. Okay, it's running. And then, so let's look at what the data looks like. So this is the training set, and we can see that it's 5,500 images, or 55,000 images, and each one is basically 784 values big, and that corresponds to the number of pixels in each image. So if we look at this is a sample, one of the sample images. If we look here, we'll see a bunch of zeros. That essentially corresponds to a white pixel. And then the these values here are basically a value between 0 and 1 of how dark that pixel is. So it's basically a monochrome image. And that's how we're mapping the data to the pixels to a tensor. You would do this differently for an RGB image, but this is essentially a grayscale image. And then we can basically use like matplotlib to like take the input image and show what it looks like. So this is just this particular image is an 8. And then we can look at the labels. And if we look at the labels, we can see that each label is 55,000. There's 55,000 labels, each one for each value in the train set, and they're 10 big. So each one of those 10 values that you get out is basically, it's a hot 1 vector, or what's called a hot 1 vector, where you have all zeros except for one value, which is a 1. And that's basically saying that we know what the value is. We know this particular value is an 8, so we're going to say it's 100% that it's an 8, and 0% that it's everything else. So when we look at the actual value, we can see that we've got a 1 in the one column, which is basically saying 0, 1, 2, 3, 4, 5, 6, 7, 8, 100% that it's an 8, 0% that it's a 9, or everything else. And then here's just like some images that I showed you earlier. But this is basically what I'm going to do is a very simple example where I have a single layer in my network. And then what I can do is the weights and the biases will actually be the weight for whether if a pixel is dark, whether it corresponds to a percentage value that particular number is or that particular image is a particular number. So for this particular example, not for all examples, but for this particular example, you can actually take this and show the weight and how it corresponds to the actual value coming out. So if there's a pixel in any of these blue areas, that actually adds to the percentage that it's a 0. And if it's in one of these red areas, that negatively impacts the percentage that it's a 0. And the same for all of these other values. And so what you get out of that is you kind of get something that looks similar to what the output or the actual number looks like. So this is a 0. This one's a 1. Maybe you have some ones that look diagonal. So that's why it looks like this. Then there's a 2. This one's a 3. This one's a 4. So these kind of look similar to the actual number that you get out. But this is also, right, it's a very simple example. If you get a little bit more complicated, you won't be able to visualize it in quite the same way. But essentially, next what we can do is we can build our neural network. So this is actually where the meat and bones is, or meat and potatoes is. So here we have the placeholder value, which is our input image value. Then we set up 2 variables. This is our weight and bias. And then we're initializing the sizes of these. And then what we're going to do is define the actual network. So here we have a matrix multiplication on the weights to the x input value, and then we add that with b, which is our bias. What's really interesting is that we can just basically initialize these to 0. We don't have to have a weight or bias initialized at all. We can determine the weights and the biases by training the model. So we can just initialize these as 0 and then start training. Then we're going to use what's called a gradient descent algorithm to actually take the loss and then map that to changing our weights and biases as we're doing training. So here we're using a method called cross entropy to get our loss function, and then we're going to train using this gradient descent optimizer. So what that does is, at a high level, is it can take the value that we get out and then try to minimize the function. So this minimize the loss function will give us out an error rate, which is like maybe between a 0 and 1. And we want to minimize that, get that as close to 0 as possible. So get the difference as close to 0 as possible. So our gradient descent optimizer will basically be able to nudge our weights and biases in a direction that will make the loss function go down, right? So that's essentially what it is. You can imagine going down a mountain with a little flashlight and kind of trying to find the bottom of the mountain. Obviously, you'll hit things like local minima, but in general, it's a pretty good algorithm. So then, what we can do is run our actual training. So here we're going to create a session and then run our actual training. So we're going to do mini batch training. So this is going to run 1,000 times on a batch of training data. And what's really cool is that each time we run through this batch training data, we only have to train on 100 values, right? We don't have to train on all 55,000 values. We can just pick a random set and then train on that. And when you do that, you essentially get very close to as if you trained all of the data on all of the data. It's kind of like as if you, instead of asking all of you how old you are, I ask a random number of you how old you are and take the average of that instead of averaging out everybody's values. And so that way I get a representative example. So that's a little bit of a representative sample. So that's a little bit of statistics magic, but essentially that'll allow you to save a lot of work. So once you've trained that data, you can then run a prediction run the prediction on on some test data, which is like the training data. We know that the actual values for the training, the same as the training data. Our test value also has labels associated with it, so we know what the correct value is. But we run it through the prediction, and we actually check the values to make sure that they're accurate. And then we see that our model is about 91% accurate. And you can make this, the state of the art is about maybe 99.96 or something like that % accurate. But you can get pretty far with just a very simple model like this. So if you're interested, definitely check out tensorflow.org and check out all of the examples and samples that they have there. It's a very good resource. And if you are interested, you can kind of find me after the conference as well, because I'll be around and kind of ask me questions then. So thanks a lot.
Thank you very much. Time is end. If you have any questions, please ask him to later.
Yeah, I'll be hanging out here. Like if you want to ask questions outside the door here or something, I'll be around.
Okay. One more time. Thank you very much.
Thanks a lot.